Test. Test. Good morning. How does it sound? Okay? Too loud, too quiet? All right. Well, I always put some instructions on the first slide, so keep you busy. Yesterday, you already have answered this question, but I want to ask it again to compare the distribution, see how the night off might affect your thinking. So please, you can reuse your previous answer, or you can rethink your previous answer. Let's just for a second check that we can see. Yeah, WebAssign seems active. What do I do? Here. All right. We'll see. The whole point of answering the question is to help you to process the information related to that. If you just randomly choose whatever answer you want to enter, without thinking, that's not going to help you to master the related material. And trying to just go ahead and answer the questions also not the best strategy. Eventually, just out of curiosity, once in a while I check WebAssign. Well, WebAssign, NSA, it doesn't matter. They know everything about everybody. So when did you answer? What did you answer? What specific time? So did you answer this question before it was asked, during, after, technically? Everything. This is not an anonymous question. This question is connected to your name because, well, I'm not asking here and now any personal information. Yeah. So let's see the distribution. I remember, well, if you looked up the slides from yesterday, the distribution had the answer number 1. Yeah, number 1 answer. Now again. Okay. Well, that's actually a good sign. Yeah. But you know the saying, trust but verify. That's from yesterday. Today. So first of all, let's take a look at 1 liter. It's kind of handy and helpful to know how it looks like. This is 1 meter. So we talk about volume. In International System of Units, 1 cubic meter is the unit of volume. A 1 cubic meter looks like this. A cube, which has 1 meter one side, 1 meter another, and 1 meter height. This is 1 cubic meter. This is, well, how many liters? 2. So what do we need to do if we want to look at 1 liter? Exactly. Oops. Buy Coca-Cola. science is a struggle. So this is how 1 liter looks like, about, as you see in the picture, 10 centimeters by 10 centimeters by 10 centimeters. And what we really want to do is basically calculate how many of these little boxes can we fit in 1 cubic meter. That's what the conversion factor is about. Yeah. If we use international system of units, we're going to make a transition from this to this. And clearly, 1, 2, 3, 4, 5, 10. 10 would not be enough. Right? As this is how much of the volume we need to fill in. And 10 times 10, 100 probably is not enough. Well, we know what to do because we know how to calculate the volume of a cube. All we have to use is geometry, right? So 10 centimeters, 10 centimeters, 10 centimeters. The volume equals length times width times height. 10 centimeters times 10 centimeters times 10 centimeters. That gives us 1,000. And if we go back, question like that was question number 2, yeah, by popularity. But what's we missing here? The unit. Is it a centimeter? No. Well, first of all, if we look at all these units, none of these represent the unit of volume. You wouldn't even have to calculate anything. But none of the above is absolutely immediate answer, because the answer must have a unit of volume. And that's not the unit of volume, neither. So what's supposed to be, well, the right unit? Centimeters times centimeters times centimeters. In algebra, it's cubed. So, well, but that's not what we are looking for. We need meters. Well, there are 2 ways to approach this situation. Number 1, number 2. Number 1, we can start from scratch. And we can measure each side in meters first. 10 centimeters in meters. What should I write? Yes. 0.1. We have to use a conversion factor, which is not listed here. So we have to kind of keep it in mind. 1 meter is equal 100 centimeters. Oops, I said it right. And if I want 10 centimeters, so over 10, 1 over 10, 0.1, 0.1, 0.1, 0.1. Now we can use the same calculation, length times width times height, 0.1 meter, well, 3 times cubed, 0.001 cubic meter. But probably most textbooks would write it using scientific notation, 10 to the negative third cubic meters. And of course, there's another way to do it, using conversion factor in this answer. Oops, why cannot erase it? Okay. So, same volume. It is the same volume. It is 1,000 cubic centimeters. But again, now we can use a conversion factor between centimeters and meters. 1 centimeter is what part of a meter? Well, if we start from the same conversion factor, and we need 1 on the right, so over 100, over 100.01. And that's supposed to be cubed. Now, if you do the math, we get the same result. 1,000th of a cubic meter. That's what 1 liter is equal to. But we don't like negative numbers in general. So how do we get rid of the negative power? We'll just multiply everything by 1,000. And that gives us a very convenient, easy to remember factor. 1 cubic meter is equal to 1,000 liters. So if we have a cube 1 by 1 by 1, we can fit 1,000 liters in it, literally. That's what it is. Any questions? We already used, just a minute ago, some information of this chart. For example, centimeter. Yeah. In physics, lots of units have a certain prefix, centi, for example. Where is it? There. Means 10 to the negative second. So it means 1/100th. And you don't have to memorize all of them, but very commonly used prefixes are deci, centi, milli, micro, nano, pico, kilo, tera, giga. In this example, yeah, we say 1 kilometer. What does it really mean? Well, this letter K tells us what it actually means. It is a conversion factor, kilo. Kilo means 1,000. So 1 kilometer is 1,000 meters. Any questions? This is just something to keep in mind. Because very often data would not be given explicitly in using international system of units. You would see a symbol like this, micro, for example, giga. Now we're going to talk about physics per se. And we start from motion because that's what we see when we look around. When we just open our eyes, when we're born, we see moving things. They exist. And existence means they occupy some space around us, and when they move, they change the location in time. It was here, now it's there. That's what the motion is. And we need to develop a specific language which we can use to describe this phenomenon we call motion. Of course, develop means no, we don't invent any new words. We just have to learn the words which already have been invented for us. And one of the properties of object is its size. Small ball, big ball. In kinematics, size doesn't matter. We can imagine that all those objects are very small, or we can just look at one specific point, how it moves in space and time, and describe that motion. That's it. Well, I will ask you a question. Yes. But first I need to prepare the demonstration. I need a piece of paper. Now red should be here. Yellow, silver. Now, those guys don't see what's happening. I know that. Wait, we need to fit it. So please pay attention to what's going to happen. I've been trained hours for doing this. The experiment starts now. Do you want to see it again? All right. Long and important preparation. Experiment. Now, please tell me what you think about this question. Anyone can jump in. Yes? Have you been taking physics before? Well, high school is before, right? So you've taken physics before. That's cheating. But I saw some people confused. Yes, this is a situation when the answer depends on the context, and context is not clear. And when the context is not clear, it's your duty to clear it up for you. Instead of thinking, you should be asking, Mr. V, you didn't specify relative to what? So you should ask me, relative to what should I consider the existence of this yellow object? Then I will clarify relative to, and I will say something, and then you can say, okay, relative to that, it was or was not moving. That's how it works. So relative to what do you want me to clarify this question? Anybody? Relative to what? Ask me a question. Mr. V. What? If you think it's you, it's you. That's the rule. Yes. That's it. Very simple. So this experiment is very trivial, but it has to be imprinted in our memory. Motion cannot be described in general. It must be described relative to a specific set of objects which we choose. Those objects have a name, reference frame. There is an origin, the central object, and some other objects like XYZ axis, but without saying specifically that we want to analyze the motion relative to this reference frame, everything else is meaningless. However, no one ever writes it down explicitly in textbook when you have to solve a specific problem, because it's assumed, it's meant that unless opposite said, motion of everything is being considered, analyzed relative to the ground, relative to a specific object on that ground, like a tree or a building or something else. But we will talk about situations when the motion will be analyzed about, well, relative to different objects, which also may be moving relative to each other or ground. Technically, everything is moving relative to something. We all right now move relative to the sun. We cannot forget that when we we have to able to say, my analysis of the motion of those objects is relative to, and we have to say what. Now, it's not an art class, so we have to figure out simple, easy to use ways to visualize, to represent that motion. And one of the easiest, simplest approaches is just to show the location of the same object at different instances. And, well, okay, we cannot go back in time in real life, but here we can. So at initial instant t equals 0, when we start the stopwatch, some small bugs on the ground relative to the tree, and then it moves and moves, and every 5 seconds it moves away and away. And we need to be able to describe that in words. For example, we have to say, all right, this box is moving to the right. It doesn't move up or down. Relative to you watching on the whole picture. And the next step, we can put together all those like snapshots. And this picture has a special name. We call it a motion diagram. It's a diagram which represents the motion of an object. We can see the location of that object at different instances. Here, those instances are 5 seconds apart. And if we look at the motion diagram, we already can say something important. From our everyday experience, we can say it moves faster every next time, every next 5 seconds, because every 5 seconds, every same time interval, it travels slightly larger distance. That's what we used to call speeding up. So a motion diagram is very informative. But the next step, we can connect all the dots. We can connect all the locations. And this line represents the path. But in physics, we also call it trajectory. A trajectory is the line of the motion of an object. That's an official definition. Now, a trajectory is a line. And we know many types of lines from geometry. Straight line, circle. This one is a parabola. Circle. So depending on the shape of the trajectory, we can classify those motions. And when the trajectory is a straight line, the motion is called one-dimensional. We need only one number, one dimension to represent the location of an object relative to that line. And we can just take a measuring tape, choose the 0, let's say here, point the measuring tape along the path, along the trajectory, and then read the numbers. Those numbers we call coordinates. Now, if the trajectory is not a straight line, but lies in a plane, like again, this one, we call it a two-dimensional motion. And, well, something like this. Oops. We call it three-dimensional motion. Thank you. Thank you. We're not going to study three-dimensional motion, not because it's too difficult, on the contrary, because it's actually doesn't give much new information relative to one-dimensional and two-dimensional. And now we need to introduce more physical quantities useful for describing, well, in general, any type of motion, specifically one-dimensional, two-dimensional type of motion. So First term, distance. An official definition of distance is the length of the trajectory. That's what it is. So if this ghost flies using path D to get to the treasure chest, and we ask what distance traveled, we have to say, okay, distance is the length of the trajectory. Trajectory is the line which represents the motion. So the path D begins here, goes like this, like this, like this, like this. So we need to figure out how long it is. How can we do that? Well, we have options. We can use measuring devices. Write it down. Or we can use the fact that length is an additive. So we can break the path in smaller parts, measure the length of each individual part, and add a map. For example, here the length equals 2. 2 what? Well, 2 blocks. 2 blocks. That's my unit, B. This length equals 2, 3, 4, 5, 6. 6 blocks. 1, 2, 3, 4. 4 blocks. 1 block. Total length will be equal to 2 plus 6 plus 4 plus 1, 13 blocks. Done. Now, if we know a conversion factor, if someone tells us 1 block equals, I don't know, 30 yards, we can convert this distance into yards or then meters or anything else we like. Displacement is a trickier word because it has more meanings. First of all, displacement means an action. We are displacing this from here to there. It's been displaced. But if you read any textbook or any problem, displacement usually means the distance from the initial point to the final point. And that's actually wrong. That's not an official definition. But that's what usually people mean. So start, that's what we call initial location. Finish, that's what we call final location. And normally when people say find displacement, they would mean distance from start to finish, this distance. But an official definition of a displacement is this. A displacement is an arrow which begins at the initial location and ends at the final location of an object, points from initial to final. An arrow, like this. So find the displacement means find that arrow. But that arrow, as any arrow, of course, has length or absolute value or magnitude, depending on how you call it at school. Also, it points somewhere. It has a direction. To describe the magnitude of displacement, well, we need to measure this distance. And that's what people call displacement very often. They call it displacement, but mean magnitude of displacement. To describe the direction of this arrow, we can use, well, we can use geography, or we can use a specific device we call, how do we call it? Protractor. If we use the protractor, we can measure angle between a certain direction, usually horizontal line. We call it x-axis. This angle can be measured, and in physics, it's some Greek letter alpha. And this number, like 30 degrees, describes the direction. So now, please solve this problem. using the definitions we just have learned, we can solve this problem. So please get a number, and this is what I'm going to do. I'm going to wait for you to solve it, and when you get a number, please just wave. And when I see that many people are done, in that case, I'm going to ask for your answer. We will discuss it. Thank you, thank you, thank you, thank you, thank you, thank you. What's your answer? That is not a tricky question. Yes, the answer is 7. So what do we have to do? We have to follow the steps of the problem-solving process. We have to read. Then we have to, shall we here, draw a picture, west, south. This is 4 meters long. This is 3 meters long. So what are we looking for? Distance. What is the distance? Distance, distance, distance. Length of the trajectory. So 4 plus 3, 7. Done. Next question, please. And now, after solving this problem, you should enter your answer into the WebAssign, Lecture 2, question 3. So when I return to the podium, I will switch from this slide. You will not be able to see the problem anymore. I will be looking at the WebAssign. So you should, yes? I don't understand the question. Please ask again.
So, after walking 4 meters,
Yes.
and say you didn't tell us what, like, your how do we figure out if it's
Well,
or will you always tell us?
I don't know. What I read is the word south. It says right here, there, right there on the screen.
But it'll always be given, like, can you tell just from the angle?
Okay, so your question is, if I know the angle and no other information, how would you know if it's south or north? You wouldn't, of course. You need that additional information. So when you walk and you make a 90 degrees turn, you have two options. You can make this turn, that turn. If that information is not provided, it's your duty to require the additional information. If you don't do your duty, you're not getting paid. So I'm switching. That's the question number 3. I'm still working. And we have certain distribution. You know what I want to check? All right. So 5 is the most popular answer, but some people decided to mess with me. Don't do that. All right. Well, if we need to solve a problem, we have to follow the problem-solving procedure, which is the same for every person, for every problem. If that would have been a course for physics teachers, I would spend the whole lecture walking through each individual step of the process. Good thing you're just doctors. No one wants to be a teacher. So just follow the reasoning, just follow the strategy. We start from telling ourselves what's happening. So you, now in this situation, it's I. I walk. And then I make a turn here. I look to the right, I look to the left. Okay, I want to go south. This is my trajectory. And that's my initial point, start. That's my final point, finish. And that's it. That's what happened. Now, what are we looking for? Displacement. What is a displacement? What is an official definition of a displacement? A displacement is an arrow which connects the initial point and the final point. An arrow. So, I found the displacement. That's it. I'm done. No, of course not. Because in a textbook, when people write, what's your displacement, they mean what's the magnitude of that. And I specifically write, find the magnitude of that. The magnitude of a displacement is a number. The magnitude of the displacement is the length of this. Well, actually, most commonly people use a letter S. That's what we need to find out. All right. Now, this is what I have. I know this side is 4 meters long, this side is 3 meters long. Where else do I know? Well, I know that north, south, east, west, they actually, those directions perpendicular to each other, all of them. So the angle between west and south is 90 degrees. Where is it? Here, here. All right. So what I am looking for, this. Now, I need to relate. What do I need to relate? I need to relate, well, let's call them A and B. I need to relate what I know and what I don't know. I need to bridge the gap. Now, what do I have? The only thing I have is this figure. So I have to think, what do I know about these figures? Well, first of all, what kind of a shape is that? Is that a circle? No. Is it a trapezoid? No. What is it? A triangle. All right, what do I know about triangles? Triangles, acute, obtuse, right-angle triangles. What kind of is this one? Right-angle triangle, okay. Good, getting closer and closer. If it's a right-angle triangle, now I gotta ask myself a question. What do I know about right-angle triangles? So, please tell me, what do we know about right-angle triangles? Yes? What's the name for this equation? Pythagorean theorem, all right. What else do we know about right-angle triangles? Yes? So we can relate angles using specific geometrical functions like sine, cosine, tangent, and length of each side. So we have many, many equations. There is one word which we can use to answer this question. One word which answers everything you said. What do you think that word is? Yes? What do we know about right-angle triangle? One word which says Pythagorean theorem, which says sine, which says cosine, which says tangent. Everything. we know everything about right angle triangles, a lot of information. And now we have to choose what piece of information can we use from what we know to finish the solution of this problem. So we need to relate side, side, side. And that relationship doesn't involve any specific angles. We can call them alpha or beta, actually usually like this. But it involves sides. And the Pythagorean theorem tells us how these three sides are related. Now we can do some algebra, because we ask a question, okay, I know this, I know this, so that gives me this, so that gives me this. Are we done? No. This is not what we need to calculate. What we need to calculate is this. So we have to go back in time again, I don't know, 8th grade. How do we get from something squared to unsquared? Well, we got to apply a specific action, has a name, square root. Yeah, we unsquare it. Square root, square root. Technically, when we do this operation, we have two answers. A square root of 25 is either positive 5 or negative 5. But this is not just abstract algebraical equation. What we're looking for is distance, length. Length. So can length be negative? No. So we eliminate the wrong answer. Five. And of course, it's an easy problem. But if you can extract the problem-solving strategy, we can apply that strategy to solve any problem in physics. Any questions? Well, that's what we know. That's a readable slide. Please tell me what you think. There's a statement in quotes. 3, 4, 5 triangle is also a 30, 60, 19 triangle. So as every statement, this statement might be correct or wrong, too general, vague, you know. So what do you think? You know, yesterday we haven't been doing physics much. Today, well, we've been doing physics for 45 minutes. For 45 minutes, I've been tricking you. I've been asking you, what do you think? What do you think? Physics doesn't require thinking. That's what's wrong. You don't have to think right now. You have to just solve it and see if it's right or not. And solving means acting. So like taking a pen, drawing a picture, writing equations, calculating the angle and see if it's 30 or 60 or not. And you cannot do it in your head. So thinking is counterproductive in physics course. Don't think. Do. So I'm going to give you a couple of more minutes. But I'm going to switch to the WebAssign probably very soon. That's question 4. So switching. You should expect that when I have a question, I will switch to the WebAssign at a certain point. So you should use that time between looking at the screen and switching to get all the information you may need find useful from the screen into your notes. So you could use that information when you do not see the screen anymore. That's question 4. We already have some distribution. And as you can see, yes and no questions are practically 50-50 divided. One more minute. You could ask, no one asked, 3, 4, 5. Are those meters, centimeters, miles? Doesn't matter. What do you think? Yeah. Well, meters, miles, doesn't matter. It doesn't matter. It could be 3 meters, 3 millimeters, 3 miles, and 4 and 5. As long as they have the same unit, that doesn't affect the angle. It just scales up or scales down the whole picture, but it doesn't affect the angles, right? So, one more glimpse. Still, yes or no, divided practically evenly. Well, all right, so this is what we got to do. Oops, wrong pen. Right, we got to draw the picture. In this picture, we know the sides because we just have it solved. Actually, you know what? You okay with that? You should not be. You should pay attention to details. What's wrong with this? Yes? No, the right angle is right here. Might not looking like very right, yes? Yes? So I made a mistake. I told you I will be making mistakes. So you have to pay attention. Of course, the shorter side should be equal to 3 wherever, and longer should be equal to 4 wherever. That affects the values of angles. So now we have to choose whatever angle, well, theta we want to calculate. Now we have to choose the equation which relates this angle, theta, and one of these, well, we call them, let's say, A, B, C. One or two, all 3 of these sides, A, B, and C. So that's what we know. That's what we're looking for. We have to bridge the gap using the information available to us. So you have to pick an equation. The equation which would give you a way to calculate that angle. So pick an equation, please. Do you want to use sine, cosine, or tangent? Cosine. All right. So cosine of this angle should be equal to, according to this equation, it should be equal to the ratio of B over C. In numbers, well, you know what? Question 5. Solve and select your answer to question 4. So the same question, the same set of answers You just now please enter into the next available slot, number 5. So I don't change the question, I change the number of that question. Yeah? I'm asking the same question twice. It was question 4, now it is the same question, but now it's number 5. And now you have some extra guidance. Use it. So, these are some standard values. Again, you don't have to remember those, but since we talk about angles, 30 degrees, 60 degrees, cosine of 60 degrees equals a half. Cosine of 30 degrees is about 0.867, 0.7. There are standard angles which are very commonly used, 30, 60, 45, and it's handy to just have in your memory or in your notebook the values for sine, cosine, and tangent of those angles. Sine of 30 equals cosine of 60 is a half, etc., etc. You can look it up. One of the, yes?
How do we submit this answer if you just fill in both?
You submit it into question 5. No, you choose from the same set of answers. You use your number which you found to answer the same questions. See? The questions are the same. The question is the same. The answers are the same. But now we have done some extra thinking. All right. Well, you see, distribution has changed. So before doing, the distribution was even. Now, after doing, the distribution is different. Different right. This is not a 30, 60, 90 triangle. So please keep it in mind that thinking what you've been trying to do first is not helpful. Doing helps. Yeah? And I have proved it right now by comparing two distributions, before doing and after doing. So we can finish this calculation just for the sake of finishing it. So that's going to be 4 over 3. And now, technically, we are looking for the angle. So we have to use the inverse cosine function. The angle is the inverse function of that. And at this point, we also need to use a calculator. Oh, 5, yeah. Did I tell you I hate morning classes? And I would usually use tangent, actually. It's in my brain. So now we gotta, well, and you need to know how to use your calculator quickly without thinking. Because on the exam, if you start thinking, about how to calculate something. That precious seconds which you may lose on something insignificant. So my calculator uses second function, cosine. You have to use parentheses at 4.8 equals 36.8 or about 37 degrees. So that's going to be, if this is 37, this angle, anybody, is equal to it's your time. Until someone says the number, I'm just going to wait. 53, thank you. How did you find it? What rule did you use? That's a rule. Yeah. But that's not obvious. That's a rule. We have to know it. So if you have a triangle, any triangle, so alpha, beta, gamma, the sum of angles, always 180. And this rule might be handy sometimes in the future as well. All right, so we talked about position, how it changes, displacement, distance, etc., etc. Of course, next natural question is, how do we describe how fast position changes? How fast displacement changes? And we could spend 300 years to figure out what would be the best physical quantity to describe how fast something changes, or we can look it up and use definitions which have been developed, prepared, tested, and work very good. Two definitions are on the screen, and a definition is something we just have to remember. A definition does not require understanding. There's nothing to understand. It is something to memorize. First one, average velocity. That's a name of physical quantity which we use to describe how fast displacement changes. And a definition of that, it's equal to displacement over time. Of course, we don't use words. We use algebraical variables. And a standard symbol for average velocity is a letter V with a little arrow. An arrow tells us it has a direction like a displacement. But contemporary textbooks, they don't usually use an arrow anymore. They use a bold italic font to represent that it has a direction. Displacement, well, that's a standard mathematical symbol for a displacement. I would use just the letter S. And time for that displacement to happen. That's it. Second definition, average speed. And average speed is defined using a distance. It tells us how fast distance changes. And according to this definition, it equals distance divided by time. That's it. Those are definitions. You just need to remember those definitions. And the difference between these two variables, speed is a number. Velocity is not a number. It's something more complicated because it has a direction. And everything which has a direction we call a vector. And we're going to talk about it probably tomorrow. Question? We just have learned two definitions. And now we can use those definitions to solve specific problems. For example, this one. An object was traveling. Well, we could say west, we could say to the left. Normally we could say toward negative x direction, because that's usually assumed. So how far? 4 meters. Then it makes a turn, and it travels south. How far? 3 meters. It took 6 seconds to travel left. It took 4 seconds to travel down, we need to be able to use many different words to describe the same action, the same movement, the same motion. And now after, yes? I cannot hear you, please. Of course, now everything shifts. If you try to enter question number 5, you just wouldn't be able to do that. So that prompts you to move ahead to the next number. That's it. Thank you. Good logic. Yeah, I didn't think I would ask you the same question twice. And then I decided, why not? And I did. So, you, of course, know by now that the first action is drawing a picture which represents what's happening. And then that picture should give you important hints how to use that information provided to you to answer the final question. So the question is about average velocity. If you have two definitions, one about average velocity, second about average speed, and you need to calculate average velocity, the definition of what do you use? Well, you're jumping ahead. Yeah, of course, you would have to use the definition of average velocity, not average speed. But then, logically, to use the definition of average velocity, you would have to use the definition of a displacement, find it, plug it in the equation, do some arithmetics, done. Well, we already have many answers, so I'm going to switch back. Well, I don't know how to draw a fly. Something like this. "4 meters west." That's, I want to call it distance traveled west. 3 meters south, I want to call it 3 meters south. So distance traveled south, 3. Done for now. This is 90 degrees angle. Now, magnitude of average velocity. So this is how I wrote it. In a standard regular textbook, it would be something like, find average velocity. That's it. So you have to know that what they mean is calculating a finite number which represents the magnitude of average velocity. So average velocity, what is the definition of that? Well, I use a letter S for the displacement and just a letter T for time. We can use any letters we like. And now, displacement S, I don't see it. If I don't see it, I can't find it. To find it, I have to see it. To see it, I have to draw it. Done. That's displacement. Do I know it? Yes. I don't have to repeat all the calculation. It's in my memory cell now. I know it will be 5. So that's 5. And time. time. So it took 6 seconds to travel one way and 4 to travel another way. So that's going to be 5 over 10.5. Now, I've been using meters and seconds. So my unit for the velocity automatically meters per second. Now, what I did here, I didn't write mathematical symbols, which I assumed. What should have been written is this. Absolute value of average velocity should be equal to absolute value of the displacement over time. But since I know what I'm doing, I don't write vertical bars, which represent magnitude. I don't draw a little arrow, which represents direction. I know they are there because it saves time. That's it. It's more convenient. Yes?
Would you want to see the absolute values or not symbols on lab?
No. As long as you know what you're doing, because if you don't know what you're doing, your answer will be wrong. Well, since we're on this, if we want to calculate average speed, we would have to use a different definition. And speed equals distance over time, and distance will be length of the trajectory over elapsed time, 6 plus 4, so 0.7 meters per second. We can see, actually, numbers are different. We cannot assume that average speed and average velocity are equal because we just proved it might not be a case. All right, so again, depending on trajectory, we can study one-dimensional motion, two-dimensional motion, three-dimensional motion, but two-dimensional motion is just a combination of two one-dimensional motions. So if we know what to do about one-dimensional motion, we know what to do about any dimensional motion. So we have to spend some time on study one-dimensional motion. And to do that, we have to look at one-dimensional motion. And, well, one example of one-dimensional motion everybody knows is this. Well, close to one-dimensional. Up or down, that's a vertical motion. That's horizontal one-dimensional motion. But a very commonly used device is cart on a track. You're going to use this in the lab today and tomorrow. And all we need to do is just tilt it. Now if I say release it from rest, it starts moving. And I can play with this. I can give it a push and see what's going to happen, see how it's moving. And we can describe this motion using words, and we can describe this motion using numbers. For example, every track has a measuring tape, but instead of using rulers, we use a contemporary device, a motion, ultrasonic motion sensor. It makes ultrasonic pulses. They travel, get reflected, travel back, and there's an interface which connects this sensor to a computer, and we can use that interface to measure instantaneous location of this object. And then if we know instantaneous location, we can calculate velocity, acceleration, everything we want to. So what can be done? What can be measured? What can be calculated? So first, if we know the coordinates, these numbers for different times, we can plot a chart. At t equals 0, object was, well, in my example, like 1 meter away from the origin. And then at t equals 5, 61, etc., etc. What can we do with those numbers? Well, we can plot a graph. Plotting graphs and reading graphs is an important skill. So here, how do we do it? Well, 0, 1, t is supposed to be equal to 0, x is supposed to be equal to 1. This dot represents this reading 561. Time is supposed to be equal to 5. It's not to a scale. 61. This dot represents this reading. Now this is a graph, an abstract mathematical object. This is a set of photographs, what we really see. And they are related by this chart. Then we can connect those lines, and we can see it doesn't look like a straight line, which is natural. We will learn today or tomorrow why. But we also can use certain software procedures, mathematical procedures, to extract information from the graph about the equation. Interpolation can be done. And now, when we know the equation, we can make a prediction. That's what this is about. We can ask a question. For example, where will this object be at time equals 37? So we just have to plug in 37 in this equation, take a calculator, calculate, and that will be the answer. So, first of all, for many people, selecting axis horizontally is a natural choice. But in this situation, that would be a bad choice. Because when we analyze one-dimensional motion, it doesn't matter, if it's vertical, horizontal, or anything else, we should point the x-axis. We should choose our ruler along the path. In that case, we need only one number to know, to demonstrate, to analyze, to describe the location, the instantaneous location of this object. Well, now let's see what we can get from that. This is so-called Lager-Pro-Vernier software, which goes with the equipment, and it's pre-installed, of course. You will see something like that, and if you want to use it, okay, here. All you have to do is click collect. Where is the origin? I have no idea. It's in there. But I can set it up if I want to, and the teaching file is supposed to describe how you can do it. You can choose 0 at any initial location. So it's a little bit inertial. You can hear, if you're close enough, when it starts measuring, it clicks, clicking. It makes clicking sound. Clicking means it's working. So what we have, is it a trajectory? What do you think? Is this a trajectory of this object? No, it's not. Trajectory is a straight line. It goes from here to there. That's supposed to be the trajectory. The trajectory is a set of motion diagrams. And this is a graph, a mathematical abstract, which relates position and time. For example, I can use this graph to I can, okay. So to read it, at t equals 3.3-ish seconds, the position relative to certain origin was equal to about 9 meters. So x t equals, well, x at 3.3 equals 9. And we can repeat this type of reading again and again and again. And next step which we can do here is, let's see if we can do here. I can hold the delete button, select the region, and try to get a good equation. Oh, that looks like a good line, quadratic equation. Okay, and I can read the numbers. These numbers give me the equation, well, for this period of motion. X equals a 0.087 times t squared plus b. B actually is looks like negative. Okay. Negative 0.08 times t plus cc, some constant. Okay. And now, if we use this equation, we can predict, well, theoretically, if this track would have been infinitely long, if it would be traveling forever, we could predict the location of this cart anytime in the future. That's how it works. All right, I'm going to try to I'm going to show one more graph. Just one more for now. We know from our everyday experience that when it travels down, it travels faster and faster and faster. We call it speeding up. It speeds up. To describe that, we use velocity. So when an object travels same distance, same time, same distance, we know velocity is constant. So when velocity changes, the object is speeding up or slowing down. So this is what we call speeding up. This is what we call slowing down. And we should be able to see from the graph when object was speeding up, when it was slowing down, when it was traveling at constant velocity, or even at rest. When it's at rest, the x number should be exactly the same for a certain period of time. Yeah? When x changes, it moves. So let's try both at the same time. So we can say this motion has two different intervals. First, it was slowing down, right? And then it was speeding up. And actually, to get from slowing down regime to speeding up regime, it had to stop. That's the point of the maximum displacement, the point of reverse. And we can see in the graphs how was it happening. So at first, it was slowing down. Here, it, for a fraction of a second, stopped, and then it started rolling back in opposite direction, but faster and faster, speeding up. And for each interval, or for the whole thing, we can make selections and find the equation which describes how coordinate changes in time. This equation actually has a name, the motion equation. But here we also see how velocity changes. This graph represents velocity. And velocity, you see, in this situation, is given by just a straight line, but not horizontal. Because horizontal line, horizontal graph, would represent same velocity, constant velocity. Here, velocity was not 0. Then it became 0 at this instant. And then it's not 0 anymore. Here, velocity is negative. Here, velocity is positive. What does it mean? It means that here, well, if we draw the motion diagram X, and this is a cart, when velocity is negative, it means it was moving opposite, well, to positive X direction. And in your lab, the positive X direction automatically set to direction away from the sensor. So relative to me, to the right are positive numbers. So 0 was somewhere there. I could set it differently, but it doesn't matter. And in that direction from 0, numbers are negative. In this direction from 0, numbers are positive. And here, it was traveling opposite to positive direction. And then it was traveling in the positive direction. That's what we see in this graph. We're going to talk more about reading graphs and how extract information from those graphs. But this is already sufficient for you for the lab. So again, many questions can be answered using this. For example, if we can measure location here, time 1, x1, if we can measure time 2, x2, what can we calculate? Average velocity. Average velocity equals displacement over time. Now, it's very handy to always draw a simple motion diagram. So x1, 1.4, x1. x2, 9, x2, 9. How was it moving? It was moved from x1 to x2. This is my displacement, actually. This arrow represents displacement. How can I calculate the magnitude of this arrow? Well, the magnitude of this displacement is equal to the difference between these numbers, 1.5, 1.4, 9. So x, well, technically, displacement always equals final minus initial. But if we're looking for the magnitude of it, it will be 1.4 minus 9. And time is equal to difference between these two. Well, I cannot read them here, but I could try to find 1.4, 1.4, 1.4 somewhere here. So that's E1 and x2, 9. Oh, that's not 9, that's 0.9. Sorry, 0.9. 0.9, 1.6, that's T2. T2. So 0.9, the difference here, T2 minus T1, 1.6 seconds minus 0.7 seconds, done. That's going to be our average velocity for this particular part of the whole motion. We can calculate average speed Yeah, but to calculate the average speed, we would have to use a different definition. We would need to know the distance and divide it by time. So as long as we know definitions and follow this strategy, that's it. Well, good. All right, so this is just a summary for any one-dimensional motion. We can all, yes?
On the last slide, why did you do 1.9?
Because I used absolute value symbol.
Oh, okay.
And absolute value always makes it positive. So I did it automatically in my head. Thank you. See those vertical bars? But you're absolutely correct. You could have done it without this average velocity. That would have been 0.9 minus 1.4 over 1.6 minus 0.7. That actually would have been a negative number, which is consistent, which was what's happening. Negative velocity means it was traveling opposite to positive x direction. That's it. So for any one-dimensional motion, we can always eventually write or use a motion equation, and the motion equation can be used to relate coordinates, initial, final, displacement, everything. And then we can use that information to calculate average velocity, average speed. All right, let's just solve this. We still have 1 minute. So what's happening here? Here we have a one-dimensional motion. For 6 seconds, the same fly. It's a scientific fly. Flies 4 meters west, 4 meters, 6 seconds. Makes a U-turn. So now the angle is 180, not 90. And flies 3 meters, again for 4 more seconds. So that's the initial location of the fly. That's the final location of the fly. We can calculate anything we want. We can calculate average speed and average velocity on its way to the left. We can calculate average speed and average velocity on its way to the right. And we can calculate average speed and average velocity for the whole trip. And that's what we're going to do tomorrow. Because my alarm tells we're done. Well, thank you. Yes, yes.
I just had two conceptual questions.
Yes.
So, displacement can never be larger than distance, correct?
We never know for sure until we finish our calculation. Displacement, so this distance and displacement might be equal, or distance might be longer than displacement.
But displacement can never be larger than distance.
No.
And then, we were like, I think we're going to start this next class, but can velocity be negative while acceleration is positive?
Yes.
Hi, Professor.
Yes.
I went to the lab yesterday and I took a photo. For some reason, I didn't get one. Was that lab yesterday or was it?
First of all, why did you go to the lab yesterday?
Because it was on the solar.
So,
I went.
where were you yesterday?
In the morning, I kind of like.
So you did. So you missed.
I missed one lecture.
But that's why you came to the lab, because I